Do you ever wonder how airplanes went from this to this? Or how they went from here to here? In just over 100 years, airplanes have gone from single propellers with fabric stretched over wooden wings to the flying metal behemoths we know today. For most planes, the overall shape hasn't really changed. Engines facing forward, tail facing back, wings sticking out on both sides, and hopefully at least a few wheels on bottom. But one of the parts that has arguably changed the most are the wings. While modern wing design might seem smooth and simple, hundreds of millions of dollars have gone into optimizing them down to the nanoscale. Today, we're going to be looking at some of the biggest changes. Don't forget to like and subscribe, and let's jump in. Any airplane designer will tell you that the wing is the heart of a plane. For conventional airplanes, it provides most of the lift generated by the plane, which is what allows it to take to the skies and governs most of its aerodynamic capabilities. Most of us know about Orville and Wilbur Wright's first flying machine that took to the skies of Kitty Hawk, North Carolina in 1903. The plane was powered by a custom-built engine designed off the 12 horsepower engines powering the cars of the day. The wings stretched 40 feet and were comprised of fabrics wrapped around a spruce wooden skeleton. Nowadays, most plane wings are made from aluminum, but not the same stuff holding your can of soup together. This is the aerospace grade stuff, an alloy with strength comparable to steel, but at a third the weight. Besides what they're made of, wing design has an enormous effect on a plane's capabilities. In wind tunnel tests, the Wright brothers discovered that thinner, longer wings created less drag, which explains the very thin and flat designs of their wings. This trend continued into World War I, with attack fighters taking to the skies with these thin wings. Today, we know that what the Wright brothers thought was actually the opposite of the truth. So it was wrong. Their early wind tunnel results were misleading, because they were limited to small tunnels and low airflow speeds by the engines of the day that powered the tunnels. Today, we know that the much larger sizes and airspeeds associated with full-scale flight result in the opposite effect. Thin wings experience what's known as thin airfoil stall much more often because of the air moving above and below the wing can easily collide at the back of the wing, causing drag and a loss of lift. This was first discovered by German engineers towards the end of the First World War and allowed them to build a Fokker triplane. These planes were able to climb much faster and maneuver more sharply than planes using thin wings, and it resulted in the Fokker D7 being one of the most effective fighters of the war. After the war, in the 1920s, most plane manufacturers moved towards the use of thicker plane wings. By the 1930s, most flying planes exhibited these efficient wing designs with thick wings and large aspect ratios. An aspect ratio is the length of a wing compared to its width. So basically, wings were getting longer, as lighter metal alloys allowed them to protrude further from the fuselage of the plane. The famous Douglas DC-3 is an excellent example, with its aesthetically beautiful high wing aspect ratio and streamlined thick wings. By this point, most planes were putting two engines on the wings, rather than one in the center of the plane, as was popular amongst World War I attack planes. This led to greater thrust, but as the engines needed structural support, this solidified the thicker airplane wings moving forward. Thicker wings had other advantages. They allowed for storage space for fuel tanks and retractable landing gear, and allowed the planes of the era to no longer need wires connecting the tips of the wing to the main body of the plane. This shift accompanied the transition from biplanes to the modern single-wing planes we know today. With the advent of jet airplanes in the 1940s, planes were approaching and even pushing past the speed of sound, and this necessitated another major wing modification. As engineers discovered the immense stresses that supersonic flight put on a plane's body, they also realized that as you approach supersonic speeds, shockwaves would start to appear along the length of the wings that could rip them apart. To reduce these shockwaves, they needed to design planes with smaller cross-sections. A smaller cross-section would mean less air needed to be pushed out of the way, reducing drag and reducing the effects of these shockwaves. And so in the end of the 40s, thinner wings made their re-emergence as engineers worked to make thinner aircraft profiles. And as planes broke the supersonic speed barrier in the 40s and 50s, this trend only continued. The Lockheed F-104, the first plane designed for sustained speeds at Mach 2, is a perfect example, with its very thin wings and a leading edge that was literally razor thin, all to reduce the strength of the shock waves generated. By this point, planes had come full circle, returning to the thin-wing Wright brothers designs, but for completely different flight conditions. As engineers continued to optimize planes for supersonic flight speeds, they discovered something else. Most planes previously had wings sticking straight out of the fuselage, and this was efficient at lower speeds. But as you approach supersonic speeds, this would create enormous pressures on the leading edges of the wings. Engineers discovered that by sweeping wings backwards rather than straight out, these forces could be reduced immensely. These wings would be less efficient at low speeds, but at high speeds, where the planes were intended to fly at most of the time, they were far more efficient. But then some scientists during the Cold War got to thinking, what if instead of designing a pair of wings for low speed or high speed, you could design them for both? This was a rather radical concept, as it required being able to shift the sweep of a wing mid-flight, and thus the variable wing sweep was born. If you're wondering why you've never seen a variable swept wing plane, it's because there are some serious performance trade-offs. The first and most obvious reason is that they're very expensive, so any benefits would have to outweigh the enormous additional costs. Another downside is that these planes stall rather easily, and so, unless complex high-lift wing devices are built in, long runways are required for the plane to be able to take off. The more efficient sweep angles available offset the weight and volume penalties imposed by the wing's mechanical sweep mechanisms, but its greater complexity and cost made it only really practical for military aircraft. But during the Cold War, military aircraft priorities were shifting. Rather than being made for dogfighting other fighters out of the sky, most planes, like the now iconic SR-71 Blackbird, were being engineered for stealth. And engineers found it impossible to engineer a sweep design for stealth. Even today, despite what you may think, aerial dogfights are exceedingly rare, and so stealth aircraft are still preferred above more efficient flyers. While it may seem like wing designs have largely settled into place, they're still constantly evolving. Although nowadays, the changes are usually more subtle. Have you ever noticed those vertical parts on the end of the wings? Well, those are called winglets, and they improve an aircraft's fuel efficiency and cruising range by reducing the aerodynamic drag associated with vortices that develop at the wingtips as the airplane moves through the air. One of the interesting things about winglets is, unlike a lot of airplane features, they help regardless of the size of the plane. So these days, most everything, from single-seat hang gliders to global jumbo jets, use winglets. The funny thing about winglets is they were actually first thought up in the late 1800s, but the idea remained on the drawing board until rekindled in the early 1970s, as spiraling fuel prices forced aircraft manufacturers to come up with anything that could improve fuel efficiency ever slightly. Nowadays, these extend aircraft range by about 6%, which might not sound like a lot, but that's hundreds of millions of gallons in jet fuel every year. And winglets are still evolving. The next generation of planes, like the Boeing 737 MAX, if it ever takes to the sky again, uses a set of dual winglets to further increase aerodynamic stability and lift. And there's been a lot of other cool wing innovations over the past few decades. A lot of them have to do with the transonic region. That's the area between subsonic and supersonic flight, where drag on a plane increases exponentially. One example are these thingies, called flap track fairings, otherwise known as anti-shock bodies, that were developed after realizing that drag can be minimized by having a cross-sectional area that changes smoothly along the length of the aircraft. Well, I hope you enjoyed this episode of Everything Science. If you did, consider liking and subscribing so you don't miss out on any future episodes. In researching for this video, I discovered a lot of cool planes, so if you want to see a video on those, let me know in the comments down below. Have a great day, and remember, there's always more to learn.